Hi, hello everybody. So yeah, I'm Curtis. I'm here to talk about our experiences designing, implementing, and deploying CoLTE, our community LTE solution. So a little bit of background, I'm going to start with this, which is a map of internet access throughout the world. And it might be what you expect. The blue places have more coverage, and so largely, you know, the Western developed countries have pretty good internet access, Canada at 91%. Developing countries such as India are seeing rapid growth from things like Geo, so they're now up to like 50%, which is double the growth of the last few years. And then places like Somalia with a lot of strife still lack internet access. But what may surprise you is the rate of change on this. So this is a graph from eMarketer showing overall worldwide internet adoption. And you can see it's still going up and to the right with expectations of around 54% in 2021. But conversely, the rate of change is actually dropping pretty dramatically. Over that 6-year period, roughly halving. So why is this? Well, I used this quote from the GSMA. In most countries, even in Africa, mobile operators have already rolled out 2G and 3G coverage, which is how most people get their internet access, as far as possible within the envelope of a commercially sustainable business model. Basically, it's diminishing returns. And what this means is places like the 800 million without any internet access, or without any access aren't going to be getting access. That growth has stopped. And the 3.5 billion people who have no broadband access, that growth is slowing, so they're not going to get access anytime soon. How do we solve that? Well, one potential answer has been the idea of community networks. These are networks owned and operated by the users, often in a fully cooperative fashion. And this solves the problem through addressing two key features. First is the affordability of the network. Local operators are often cheaper than commercial operators. And also the access. So people can actually build these networks without waiting for a telecom or major operator to come to town. There's a bunch of examples of these kind of networks. Guifi in Catalonia is the most well known. It's about 30,000 nodes. It's huge, and they've been doing really, really well. So my group has been working on community cellular, which is the application of community network principles to cellular networks. We do this because they're particularly well suited to the problems of rural internet access. First off, cellular networks are wide area. Secondly, they have centralized failure semantics, which is usually viewed as a bad thing in the networking world. But what that means is you actually have centralized repair semantics. So there's just a single spot to fix things, which is really important when things fail pretty regularly. And then they support common handsets. So there's a couple examples of these. There's Rhizomatica, a GSM network in Mexico. We've been working with Cocomonets in the Philippines for a long time. And then there's our flagship network, the Pagi GSM Network. This was a deployed community network as part of my thesis work in the old days. As a community of 1,500 people working with a local primary school and been operating sustainably for 5 years. It's a very successful project. However, we started to see some kind of cracks in this network. Firstly, the amount of smartphone growth in our network has been really, really large. This is a note from an ICTD paper in 2017 showing kind of 4G appearing. And it's gone up even more. So our analysis said basically in mid-2019 we'd have enough LTE phones to support an LTE network, which dovetailed really well with the fact that people were asking for internet access. They wanted WhatsApp, they wanted Viber, they wanted all these really critical services because general telephony is really expensive. It cost us as operators around $300 a month to have phone numbers, and then the users were charged for their individual calls and SMS. So the goal of this project was to say, hey, what if we built a community LTE network instead of a GSM network? Okay, so a little bit of background on cellular. The GSM network came live in 1991. The first packet service was in the year 2000, so actually not that long ago. And telecoms have a bunch of weird idiosyncrasies to them. One is that they have like identity primitives like phone numbers, and they provide interconnect to other telecoms. There isn't a BGP really. And they have this concept of a centralized core network. This is where all the core operations happen. It's called the NSS in GSM. Basically, the GSM world is just a extension into wireless of the wireline telephony world, like the 70s. And so that's GSM. That's old. We don't want to do that anymore. So we go to LTE, and it turns out LTE is actually pretty similar. They have phone numbers. They have interconnect. They have a core network. It's now called the Enhanced Packet Core. They just rename this thing every single generation. But the big difference, the thing that we're actually able to take advantage of, is the fact that LTE is IP-based. And this changes a bunch of dynamics. We no longer have these circuit switch networks. We're in IP world. We're in the networking world. We can do things. So how do we remake LTE to make it more appropriate for these kind of community network architectures? So we have a bunch of design principles that we built out from our experiences in these prior networks. And the first one is that we wanted it to be a dumb pipe. In classic LTE, you provide not just internet, but you also provide a suite of other services, phone numbers, calls, SMS, interconnect onto other people's networks, and you charge for all of it. In CoLTE, we just don't want to do that. We're just like, just no. And in fact, what we're going to do is punt all of those services to the over-the-top things like WhatsApp. So we don't provide calls, let's make calls on WhatsApp. We don't provide SMS, just send a messenger message in order to simplify our world and reduce our costs. Our second design principle is embracing the edge. In a cellular network, you route everything to the core, and that core is usually in a data center or a central office in a major urban area. And this is one of the primary reasons rural connectivity is expensive. This is one of our problems. What we decided to do is, in CoLTE, move all of that to the edge. So we actually take the EPC and co-locate it with the RAN. And then that just handles a small amount of RAN instances, which means we don't have to have a big heavyweight server either. And then we just interconnect these CoLTE networks together through traditional IP peering, which we know works. Lastly, our third design principle is to embrace cellular security. LTE has this really interesting wrinkle, which is that you have a SIM card in your phone, and it provides cryptographic primitives, strong cryptographic primitives. And this is used to identify you to the network, encrypt your link layer communications, and actually let you identify the network as well. In CoLTE, we actually just think these are great. Passwords are awful in Wi-Fi networks, so let's just not use them. Let's use your MC to authenticate you to the network and authenticate you to services on the network. And so we build that in. So CoLTE is itself an extension of the Open Air Interface project, which is a reference implementation of GSM. So in implementing CoLTE, we had to do an enormous amount of engineering to make a reference implementation into a real deal. And that was kind of the heavy lifting of this project. We modified it to do a small number of local support operations. This is things like removing the QoS bearers because we're not using them. And then created this software suite called Haulage, which did the policy functions. All of this is detailed in bloody and gory detail in the paper, so please take a look if that's the kind of stuff you want to hear about. The last bit was implementing a bunch of community-specific services for the community we're servicing, which is in Indonesia, so we need to translate to Indonesian, provide credit transfer services, and actually a local media server for sharing content locally within the community. So we rolled this network out. This was in 2018. It was again operated by the school. The most important detail of the infrastructure is that we used a 3 megabit per second VSAT, which is quite low for an LTE link, and we'll talk a little bit more about that later. We started noticing immediately a massive set of handsets. There were sort of low-end manufacturers of LTE phones that didn't follow the spec. The unique identifiers were not unique identifiers, and it kept crashing our system. So we started rolling out the SIM cards in these 10 at a time blocks. That unfortunately caused hotspotting among the users because they wanted to share their internet access. It was really exciting, which caused us some analysis problems. Okay, so the evaluation of the system. This is first a population map of what's going on. So on the left you can see where people live. On the right you can see our measured coverage. So we walked around Pagi and measured everything. The general point of this is that coverage is pretty good. People seem pretty happy. The geographic features usually limit your access more than anything else. So we're pinned up against the mountain, and so the coverage doesn't go up the mountain. Oh. Here's some traffic measurements. You can see as we add more users, this is the staged rollout, we get more usage, which is what you'd expect. But the traffic per user goes down, and this is because the backhaul is pinned to the wall. There is no extra capacity available, and so now we're starting to see congestion among the users. On the right, we have the usage of the network by day. You can see the time period where the power goes off every night, as well as the fact that people largely use the network at 8 p.m. to watch their YouTube videos after the sun goes down. So one of the most interesting analyses in the paper was this discussion on whether the value of moving the EPC to the RAN. And so this evaluation is a little bit hard to grok, so we'll go through it slowly. The total communication between the eNode B and the EPC, and the eNode B is the radio, and remember that's all on the community side of the VSAT, was 8.86 gigabytes over a 2-day period. Now the amount that went out to the internet was 6.1 gigabytes. And that means that 2.76 gigabytes of the traffic was just LTE signaling traffic. And this makes sense, right? The amount of signaling traffic depends on the number of handsets and not the actual usage of the handsets in general. So what it means is if we moved that EPC to the other side of the satellite, that 6.1 gigabytes would be all that we have available, and roughly half of it would be used by signaling traffic. So moving the EPC closer to the community actually doubled the bandwidth available to the network. So a brief set of lessons learned through this deployment. It's possible to run LTE networks on open source stacks. We're sort of reaching that inflection point where people can do this, and it's really exciting. B, users meet us halfway. My favorite thing about this was those handsets that kept breaking our network. Before we could fix the bugs, people bought new handsets because they really wanted internet. That was just the easier way to solve it. And to be honest, it was the easier way to solve it. There are bugs sitting in OAI that we didn't fix. WhatsApp was similarly sufficient. There's a 2G network in the community from Telkomsel, which is the major MNO. That thing crashed more often than ours. People in these kind of areas understand that things often don't work there. And lastly, and I think one of the most important details here, is how important being a part of that community was to our analysis. We wouldn't have known about the hotspotting behavior if we weren't in the community. And so if you just take this network level perspective, it looks like you add more users, capacity doesn't go up that much. It's only because we're distributing it from the user side. So being a part of the community and continued part of the community, you have a big WhatsApp channel where we talk about things breaking, is an important piece of running this kind of equipment. Okay, from here, we're doing more deployments. We have one up in Mexico. We're looking at Central Java and the Canadian Arctic at the moment. We're doing a really fun community-based congestion control system. Basically, how can the community help us figure out what services are most important? And then we're building out a big federated and cooperative network to let multiple people stand up CoLTE instances and have them all work together to provide connectivity. Thank you. Oh, that's an overslide. Yeah.